the notes for AP Calculus on the topic of area between two curves continued. So, we're going to look at a couple of problems here, finding the area between curves without a graphing calculator on the first one, and then with the graphing calculator on the second one. All right, so on this one without a graphing calculator, we've got three actual equations here, and we're going to sketch the graph of these three. So you can start with whichever one you want. I'm going to start with x equals 0. That's the simplest one. That's, remember, just a vertical line when x equals a constant like that. In this case, when x equals 0, let's see, that's right on your x-axis there. So x equals 0 is right there. And then we've got y equals square root of x plus 2 and y equals x there. So we can graph those as well. So y equals square root of x plus 2. When you want to find where two graphs intersect, there's two different ways you can do that. One, sometimes you can just substitute in some points and figure out graphically by finding the points where they intersect that way. Or you can also solve it algebraically and set them equal to each other. So I'm going to do that both ways on this one so you can see both different techniques that both work on this case. Sometimes one way might be easier than the other. So in this case, we've got our square root of x graph, but it's shifted up 2, so plus 2. And then if you find some easy points here, if you substitute in 1, square root of 1 is 1 plus 2, gives you 3. And then if you substitute in 4 is another perfect square, it's easy to figure out. Square root of 4 is 2 plus 2 gives you 4. So it'll be right here. And then we can graph that one. And it's always a good idea to label your graphs again. So this is y equals square root of x plus 2. And then our y equals x is just a linear equation. Notice the y-intercept is 0, it just starts at 0 here. And the slope is just 1, so it goes up 1 over 1. And you can see if you keep doing that, it'll eventually go to also to the point 4, 4. When x equals 4, y equals 4. So that's one way to figure out where they intersect over here at 4. Sometimes they might have more than one point of intersection. Oops. In this case, just one. And let's label that one, that's y equals x. Now the other way to figure it out is algebraically. Since these are both y equals, you can use substitution and substitute one of these in for the y and the other one, since they're both y equals. So if we substitute this square root of x plus 2 in for y in this equation, we'll get square root of x plus 2 equals x. And then to solve this, there's different ways, but it's probably easiest. The thing that makes it most difficult to solve is the radical. So if we isolate that first by subtracting a 2 from both sides, we'll get square root of x equals x minus 2. And then, to get rid of the radical, in this case it's square root. The reverse of the square root is squared. So if we square both sides, then that cancels out the square root, and you get x equals. And if we square this out, we get x times x, x squared. We'll have a negative 2x and another negative 2x, gives you negative 4x. Negative 2 times negative 2 is positive 4. And then if you subtract the x over, you get one side equal to 0. You get x squared minus 5x plus 4. And then you can see that factors of 4 that have to be negative 5 would be negative 1 and negative 4. Multiply to be positive 4, add to be negative 5. So it looks like we actually have two different answers for our x coordinates where they intersect. X equals 1 and x equals 4. But we can see x equals 1, they don't actually intersect at 1, do they? So the question is, why are we getting that as an answer? Well, sometimes they both work, but in this case they don't. The reason why we're getting 1, you can see 4 is the correct answer for where they intersect right here, is because algebraically, this square root graph is just a half problem, but if we square it, it actually turns into an entire sideways parabola that would go like this and then keep going. And so you can see they would also intersect at x equals 1 if that's the case. So that's what happened when we squared both sides. We turned it in from a half parabola to a whole parabola, which is why we got this other point of intersection. but that doesn't actually work there. Okay, so either way, again, some problems it's easier to just find some points to figure out where they intersect when we do it without a graphic calculator. Sometimes it's easier to solve it algebraically. Or you can do it both ways to kind of confirm your answer. Now, it's important to also draw in the region. Once you see the region enclosed, bounded again means all of these need to be a boundary of the region. Okay? All three of these. You can see this region right here is the only one that's bounded by all three. All these other regions go off infinitely. They're not bounded at all. So, here we're just going to draw a vertical rectangle somewhere in the region, a represented rectangle, and the width of that is dx. Later on, we'll go over some more advanced ones where sometimes it's advantageous or necessary to use a horizontal rectangle with the y, but we'll get to that later on. So now dx, so everything needs to be in terms of x. So our integral for the area, integral from, notice when you have vertical lines like this, x equals 0, those are never going to be on the top or bottom of the rectangle. They always end up being the lower limit or upper limit of your integral. Since it's dx, we want where the x-coordinate where it starts is 0, and the x-coordinate where it stops right here is 4. And then, looking at the rectangle, it's always the top one minus the bottom one. You can see the one on the top is square root of x plus 2, minus the one on the bottom is just x. And then that whole thing times dx. Because this square root of x plus 2 minus x, when you take this y-coordinate, which is square root of x plus 2, minus this y-coordinate, which is x, that's giving you the height of the rectangle. And then when you multiply by dx, which is the width of the rectangle, that's what gives you the area. But of course, we don't just have this one rectangle. We've got an infinite number of these infinitely thin rectangles we want to add up, and that's what integration does. It integrates or adds up all the areas of all those infinitely thin rectangles from 0 all the way to 4. And that's how it's able to give you the exact area. So the square root of x, to integrate that, remember that's the same as x to the 1/2. So when you integrate it, it becomes x to the 3/2 times 2/3. Plus when you integrate 2, you get 2x. And then minus, when you integrate x, you get x squared over 2. And then that's evaluated from 0 to 4. And then if we switch this one to radical form, it's probably a little easier to work with. So we've got 2x to the 3/2 is the same as square root of x cubed over 3 plus 2x minus x squared over 2. And then remember for these definite integrals, you always substitute the upper limit first. So you substitute the upper limit, square root of, sorry, I changed that to 2x, no, it's getting ahead of myself, that should stay 4 for now. So when you substitute in 4, square root of 4 is 2, cubed is 8, times 2 is 16. So we get 16 over 3, plus, substitute in 4 right here, that's 2 times 4 is 8, minus 4 squared, 16 divided by 2 is 8. And then subtract what we get when you plug in 0. Normally you put this in parentheses, but in this case, 0 wipes out all these are always just going to be 0. And you can see the 8's cancel out here, so all we're left with is 16/3. We don't have specific units on this problem, so you could just leave your answer as 16/3. But if we were told the units, if like each of these represented a centimeter, you could write centimeters squared. Or in this case, if you don't have units, if you want to remind yourself its area, you could write units squared. But you don't have to. All right, so that's without a calculator. Now, let's take a look at one with the graphing calculator. Okay, and I'm going to show you guys how to use both the TI-84, which is similar to the TI-83 also, if you have one of those, as well as the TI-Inspire. Okay? So you can see how to do both of those calculators. So it says sketch the region bounded by the given graph. So even though we have our calculator, we're still going to graph it on paper. And set up the definite integral. Okay, that's going to be, again, the most important part of these, setting those up. And then we're going to work out to find the area of the region. So let's go ahead and enter. I'll start with the TI-84. So let's enter that in here. So if we go -1, sorry, let's go to y equals first, sorry. And then the first one is natural log of x squared plus 2. So if you go y equals, the natural log is right next to the 4 here, natural log. And then x squared, you can go here, or you can go with the caret button and then 2. And then plus 2, then close parentheses, with the down arrow. And then notice this negative is out in front, and remember, and this one's, you're actually subtracting. There's 2 different buttons for those on your graphing calculator. Whenever you have a negative out in front, you're not actually subtracting 2 things. So you use the negative in parentheses right here, which looks a little smaller, and is written a little up above where the other minus sign is. And then 3, and then sign is right here, 2 buttons above the 7, and then we've got x minus pi, notice is right above the caret button, and it goes with the same color as the second button, so you hit second pi, close parentheses. And then you can graph it with whatever window size you have your calculator to start with. You graph them in order, so there's f of x, and there's g of x. So you can see the region enclosed is right in here. So if you want to zoom in on that, again, some regions are really small, some regions are really large. So you have to change your window size here. You hit window, and then I'm going to go from, like it fits here, -1 to 5 on the x minimax, and -1 to 5 on the y minimax. So they don't have to be the same for the y and the x. This one just happens to be work out that way where it works out nicely. So -1 to 5. And then regraph it, just so you can see that region a little better, so we can set things up so it doesn't look so small. There's our first one, there's f of x, and there's g of x. And again, we just have to sketch on paper here a rough sketch of that to help us set it up. So f of x, something like that, and g of x, something like that. Just a rough sketch so that we can set it up here and put our representative rectangle, we can see right here, dx. So let's go through the same graphing process on the Inspire, then we'll find our points of intersection next. So on the Inspire, oops. I recommend not using the scratch pad because you can't save things, whereas the documents you can. If you want to come back to a homework problem or a problem on the AP test, it can save you a lot of time. So let's create a new document. And then we first want the not the calculator. Try that again. We will use the calculator, not yet. So new document, add graphs first. And then let's go ahead and type those in. So the first one was natural log, which on this calculator is right above the e to the x button, the same color as the control button. So you hit control and then e to the x button, natural log. And then x is at the very bottom here, x squared, or you can hit the caret and 2, and then plus 2. Oops. And then you can enter and graphs that one. And then to get another equation enter, you hit the tab button is one way to get right there. And then that F2 was, again, same thing, the negative out in front has to be this negative in parentheses. Then 3. Then all the trig functions are on this trig button next to the 7. Sine x, and then we're actually subtracting x minus pi, so you use the regular subtraction button right there. And then pi on this calculator is right here, right next to the h. You can see we've got pi along with some other buttons as well. And then enter. And again, we can change our window size here. You can see the region enclosed. You could do it here, but to make it zoom in a little more, you can go menu, window zoom, and then number 1, window settings. And again, I'll change it to, and again, the negative in parentheses up front, -1 to 5 on the x min and max, -1 to 5 on the y min and max. All right, so let's look at how we find the points of intersection now. So this would be tough to solve without our calculator if we had to set these equal to each other. That'd be pretty tough, if not impossible, to solve exactly when you have natural log equal to a trig function. So I'm just going to call the x-coordinate at this point of intersection. We just want the x-coordinates here because it's dx, everything is x. A, capital A, and the x-coordinate of this point of intersection, capital B. Now let's use our calculator to find out those values. So let's start with the TI-84. So on the TI-84, you go second, calc, and then go down to, it's on the trace by the calc, number 5, intersect. And then it needs to know which curves are intersecting. In this case, we've only got 2. You can use the up and down arrows to choose between them. The first curve, you just hit enter. It's up in the upper left. It says y1, enter. Second curve, upper left, y2, enter. And your guess, you can either use the left and right arrows to move the cursor, or if that's going to take too long, you can also type in a guess for the x value. It looks like it's maybe at a half, so I'm going to type in a guess of 0.5. Let's see, it says x equals 0.5 is my guess, and enter. Or if you move the cursor, and then it gives you both coordinates, the x-coordinate here and the y-coordinate of the point of intersection. Here we're just entering the x-coordinate. So let's first write it down on paper. A equals 0.243. Remember to always be accurate to at least the thousandth place. And then let's store it in our calculator so we don't have to type it in. So you can go second, quit. Most calculators at 84 and newer 83s, you hit the store button, it will automatically put the answer, which was the x-coordinate we just got, with an arrow. If it doesn't do that, if it just puts the arrow, then instead you've got to go second, ANS, on the negative button right here, answer, and then hit store. And then choose the, notice all the letters here are constants you can store in your calculator, the same color as the alpha button. So you hit alpha, in this case A. And then it outputs it to confirm that's the right value. That is what we want for A. So now there's A. Let's repeat that process to find the point of intersection B, and then I'll go to the inspire. So second calc, number 5, intersect. First curve, again, there's only 2 curves here. Enter. Second curve, enter. And I guess these intersect at 3. Doesn't have to be that close of a guess, as long as it's closer to that point of intersection than any others. It's going to find the one you want. So we get 2.391, or you can write it to 2.392. And again, let's store that in our calculator so we don't have to ever type it in. Second, quit. Store alpha B. Okay. All right, let's go to the inspire now, see how we find the points of intersection. So on the inspire, you go menu, analyze graph, and then intersection. Lower bound this dotted vertical line, you have to put it to the left of the point of intersection you're trying to find, and click. Upper bound to the right of it, and click, and then it gives it to you right here. Here we just want the x-coordinate instead of the y. So just highlight it, so it's just the x-coordinate highlighted, then hit the var button for variable, and store variable, and then choose a letter, A, and enter, and I'll put it in bold there. So now it's stored as A, and again you'd have to write it on paper, but we already did that. And then to find the other point of intersection, same process, menu, analyze graph, intersection. Lower bound, this time we don't want to go past this one, we want to go to the left of just this point of intersection we're trying to find. Click there, upper bound just to the right of it, so the point of intersection is between those 2 lines. And then highlight the x-coordinate that we want to store, var, store variable, and then B, and then enter. Okay, so now those are stored. And then let's go back to just our graph here and setting up the integral. So then to set this up correctly, you always go left to right on the x-coordinates here. The region starts at A and stops at B, so the integral will be from A to B. And this is where you have to have written it down on paper to get credit for them, otherwise nobody but you and your calculator is going to know what A and B are. And then inside the integral, we've got the one on top this time is g of x minus the one on the bottom is f of x. So you write g of x minus f of x. All times dx. Now, if it's not g and f, you could also, if it was just y equals, then you'd have to write the whole equations in there. The negative 3 sine of x minus pi minus the natural log of x squared plus 2. But here we don't have to do that since they're defined for you. And let's see how we work this out on both calculators. So let's go back to the 84. So for the 84, you go second, sorry, not second. You just hit the math button, and then go down to the one that says fn int, function integrate. Now the one I'm showing you here is the older version of the 84. It's also the 83s. The newer one's going to have a slightly different format, which I'll show you in a second here. So for the older ones like this, you would type in what you want to integrate first is g of x minus f of x. But g of x is y2 in our calculator. So you hit the vars button for variables. Then the right arrow, y variables, number one function. And we want y2 first. Minus vars, right at y variables, number one function, y1. And then you put a comma, which is right above the 7. X, comma, then you put your lower limit, which we stored as alpha a, comma, the upper limit, alpha b. And hit enter, and we get 2.240, or that rounds to 2.241. That's our area there. Again, if you want, you can put units squared, but you don't have to because we don't have specific units here. Now, if you have the newer 84, what it's going to look like, it's pretty intuitive. If you have the newer 84, it's going to look like this. It's going to put a box there, and then D in a box there. So if it's that way, then you put A here. You can use the arrows or tab buttons to move between these. B here. The X goes right there, and then you would just put y2 minus y1 right there. Make sure though, if you're using the 84, do not just write your integral this way, just like it is on the calculator, because y2 is, sorry, actually I put y2 again. Should be y1. Don't write it like this, because otherwise y2 and y1 have no meaning in this problem except for to you and your calculator. You won't get points for that because nobody else knows what y2 and y1 are. You'd have to use what the note functions given in there. Okay? Same thing with the Inspire. Don't use f2 of x minus f1 of x when you write it down on paper. Use what they're actually called here. The only way you can get around that is if you actually define what they are. If you write f1 of x equals natural log of x plus 2, f2 of x equals negative 3 sine of x minus pi, then you could use them, but that I think would take longer than just using the functions that are already given to you. All right, so let's look at how we do that with the Inspire now. So the Inspire looks very much like the newer 84s in terms of the format. So this is just for graphing only on this window. So one way, there's other ways too, I think, but the way I know to get to another, the regular calculator is just go Dock, number 4, Insert Calculator. And it opens up 1.2, and now it's a normal calculator to get the integral along with a whole bunch of other things. Right next to the 9, see this button right here opens up a whole bunch. It has the fraction button, exponents, roots, as well as absolute value, and here's our integral, definite integral right here. So you can see the lower limit, we put A, hit tab or the arrows, and the upper limit B. And then we have these as g of x is f2, so hit the var button. You can also get A and B from here also. f2 of x, it's a function of x. And then arrow out there, minus, it adds these other parentheses for you automatically. Variable f1 of x. And then again you put dx. Enter, and we get the same answer. And that concludes the notes for AP Calculus on the topic of area between two curves continued.